Hey guys, it's Mr. Woodward going over some of these WorkEnergy bar chart examples with you. Big idea before we start is down here in the main paragraph before number 1, where it says, consequently, the sum of the bar heights for any initial condition must equal the sum of the bar heights for the final condition. So we're going to be looking at how energy is conserved in these different examples from the initial condition to the final condition, and that energy is going to get conserved oftentimes from work that is done. And we can see that relationship here, the total mechanical energy initially plus any work that's done external to the system by forces like friction or air resistance is going to be equal to the total mechanical energy in the final condition. So let's do number 1 together. Number 1 says, a ball falls from the top of a pillar to the ground below. The initial state is the ball at rest at the top of the pillar, and the final state is the ball just prior to striking the ground. Ignore the force of air resistance. So let's try to highlight some of the keys in the language here. First, it says a ball falls from the top of a pillar to the ground below. So this is talking about a change in height. And if you remember, height is related to potential energy. So potential energy, a gravitational potential energy, is equal to mass times gravity times height. So if something is going from the top of a pillar to the ground below, it's going to have a lot of potential energy initially and no potential energy finally. So we're going to show that by filling in some of the potential energy bar values. So at the top of the pillar is the initial condition. We're going to say that this ball has full potential energy, and then as it falls, just before it hits the bottom, its height reaches 0. So it's going to have no potential energy then, and I'm just going to call this 0. If we keep reading, it says the initial state is the ball at rest at the top of the pillar, and the final state is the ball just prior to striking the ground. So now we have our next clue. When we see the phrase at rest, we should be thinking about speed. So that clues us into kinetic energy. Kinetic energy is equal to 1/2 mv squared. So if the ball is at rest, it has no velocity and it has no kinetic energy. So at the top of the pillar before it falls down, it has no kinetic energy. And I'm going to show that here at the 0 mark for kinetic energy. But as it falls, it accelerates, falls faster and faster and faster. It picks up a lot of speed, and just before it hits the ground, it's going to have full kinetic energy. And then finally, there's this phrase that says, ignore the force of air resistance, which means that there's no forces that are slowing it down. So there's no like negative work that's done on the ball. The only work that's done is from the force of gravity, but that is not considered to be a force that is external to the system, because that force of gravity is always not included as part of the external work. So we can always ignore gravity as a force that's doing work on the ball. Finally, we want to check to see how the bar values compare before and after. So notice that in the initial condition, we have 5 bars of energy, and in the final condition, we have 5 bars of energy. So this phrase right here is now true. The kinetic and potential plus the work done before equal the kinetic and potential after the final condition. Let's try the second example. So example 2 says a car skids from a high speed to a stop with its brakes applied. The initial state is the car traveling at a high speed, and the final state is the car at rest. The force of friction does work on the car, thus changing the total mechanical energy. So let's look for clues in the language again. It says a car skids from a high speed to a stop. That's talking about kinetic energy. And I should have highlighted that in blue. I'm going to try to keep my colors straight here. High speed to a stop. So let's show that on the kinetic energy bar chart. We're going to start at a high speed, which means a lot of kinetic energy, and then in the final condition it comes to a stop, so we'll have 0 kinetic energy. Then it says the initial state is the car traveling at a high speed, and the final state is the car at rest. Okay, we got that. The force of friction does work on the car, thus changing the total mechanical energy. So that is some language about work that's being done. Force of friction does work on the car, thus changing the total mechanical energy. So work is going to be done. And this is going to be work that's decreasing the energy of the car, so that's negative work. I'm going to draw work in like this. Now we notice that on the left side, the total number of bars filled in is +5 and -5, which is 0 bars. That's like the net energy. And then on the right side, we have 0 bars here as well. If you're wondering about potential energy, the change in potential energy is equal to 0 because there's no change in height. The car is driving at a level road, so there's no like going uphill or downhill. The potential energy is 0 the entire time. The car's flat on the ground, so we don't have to include potential energy. We can show that as 0 before and 0 after. Let's do one more. Okay, number 3. It says a skier starts from rest on top of a hill A, on hill A, and skis into the valley and back up onto hill B. The skier utilizes her poles to propel herself across the snow, thus doing work to change her total mechanical energy. The initial state is on top of hill A, and the final state is on top of hill B. Ignore frictional forces. So let's start with this first phrase about skier starting from rest. That's a clue about speed. The skier starts from rest. That means the skier has no kinetic energy at the beginning. And then it says that the skier goes from the top of hill A and skis into the valley and back up onto hill B. So there's going to be a change in height from A to B. The height's going to drop a little bit. So let's go ahead and give the skier a lot of potential energy at hill A, which is in the initial condition. And then let's give the skier a little bit less potential energy after that, because at hill B, the skier will be less high. If we keep reading, it says the skier utilizes her poles to propel herself across the snow, thus doing work to change her total mechanical energy. So, work is being done here. This is going to increase her energy. She's doing work. She's going to propel herself forward, so that's going to be positive energy added to the initial side. So I'm just going to pick a couple bars of work that's being done. And then the last phrase says, the last part says the initial state is on top of hill A, the final state is on top of hill B. Ignore frictional forces. So let's check for balance here. On the left, we have 7 bars. And on the right, we have only 3 bars. So we need 4 additional bars. And that's going to come from kinetic energy, because when the skier reaches hill B, even though the skier started at rest, the skier will not be at rest at hill B because they're moving a little bit lower in height. So they're going to gain some kinetic energy. So I'm going to make up the difference by adding kinetic energy. I'm going to give the skier 4 bars of kinetic energy, and that will give the skier a total of 7 on the right side. And now everything will be balanced.